Hi, my name is Daria, and I'm from Toronto, Canada. And as a part of TSI this year, I did a project on using a Monte Carlo simulation toolkit to visualize a positron emission tomography, or PET system, under the mentorship of Dr. Fang. The goal of this project was to gain an understanding of the mechanism behind one of the widest used imaging modalities in the field of nuclear medicine, positron emission tomography, or PET imaging. As a part of the project, we utilized a Monte Carlo simulation toolkit called GATE, which is the GN4 application for tomographic emission, which is widely used for medical imaging simulations. We successfully visualized a brain-dedicated PET system that is currently under investigation at the Radiation Physics and Instrumentation Laboratory at Massachusetts General Hospital. And using the prototype of the brain-dedicated PET system, we were able to calculate and present the detection efficiency calculated through a Monte Carlo simulation, varying the thickness of the detector crystal. Here's an overview of the presentation. So first, going into positron emission tomography and what it actually is. PET imaging operates by detecting two gamma rays emitted in opposite directions from within the patient's body when positrons, which are produced as a byproduct of radioactive decay, are annihilated by interacting electrons. Typically, a scanning device is going to be symmetric, such as a tube or a cylinder. Unlike computed tomography, which is CT, where the scanner itself is a source of radiation, PET requires the administration of a radioactive dose to the patient to visualize biochemical changes in the body, such as heart muscle metabolism. For brain PET imaging, the most commonly used radionuclide is FDG, which is fluorodeoxyglucose, in which the radioisotope fluorine-18 is attached to glucose. The distribution of radioactivity within the patient's body is going to be reconstructed from the detection signals, and then adjustments are going to be made based on any calibration information. Coincidence detection is fundamental to PET image reconstruction. A coincidence is recorded when two detectors detect annihilation protons within a specific timing window, forming a coincidence line between these two detectors. The coincidence lines are then used to locate the emission source. In this report, we present the visualization of this visualization was calculated from Monte Carlo simulation from Massachusetts General Hospital, specifically the Sabbath lab. So going into how our simulation actually works. First, GATE. GATE is the GN4 application for tomographic emission, and it's dedicated to medical imaging and builds on the GN4 libraries. The simulation allows users to accurately model source and detector movement as well as decay kinetics, which make it possible to simulate time curves. Users define the geometry of device, and GN4 simulates and records particle interaction histories, known as hits, that occur within the detector. In this project, we utilized the GATE simulation packages to visualize the PET system. For a conventional PET system, the ring detector geometry is created with a set of commands that create crystals. Within each block of crystals, there's a cubic array of smaller crystals of a designated material. In our case, lutetium oxyorthosilicate, which is LSO. The materials database is going to be our file that consists of the chemical information for all of our necessary materials. For example, water, LSO, and organs such as lungs. Each of these materials have parameters for density, state, and the relative amount of elements of which they are composed. And over here, you can see a sample of how we define these parameters in our simulation. Several parameters of the source include the particle type, radionuclide, gamma, or positron, coordinates, direction, energy, activity, and half-life, which are all defined within the source.mac file of our simulation. The GN4 database defines lifetime using an absolute time t and an interval tracking time. Random time intervals between events that occur at a time t are sampled from the exponential distribution, where the following formula is used to find the source activity at a time t. A0 is the user-defined source activity at the time 0, and tau is the lifetime of the radionuclide. For each event, a proposed time interval is sampled, and then the shortest one is chosen for the primary generation. The overall time interval sampling is determined by the total activity of all of the sources. Additionally, we use two algorithms for positron emission. First, the von Neumann algorithm, which randomly generates positron energy based on measured spectra and the Ladolt-Bornstein tables, and equilinearity, which models the annihilation of two photons calculated using Gaussian blurring. the gate application offers both standard and a low energy package, and in this case, we use the standard energy package. Digitization in gates simulates the electronic response of the detectors to the charged particles or photons. This process uses sensitive detectors called crystal SD for internal detector hits. The digitizer chain processes the hits into pulses via the hit adder module, summing the energy and calculating the pulse positions and time. The pulse reader is then going to aggregate the pulses from different detector segments using a winner-takes-all approach based on energy. The following gate user modules within Gate were used for our simulation: energy resolution, energy window, which sets a threshold value for detection, spatial resolution, which models detector blurring, time resolution, which simulates temporal jitter, coincidence sorting, which identifies pairs of singles within a time interval and can distinguish true from random events and scattered events. And we also had the options to use secondary and electrons and X-rays, but for simulation efficiency, we decided to exclude these. To simplify the installation process, we decided to install a VGate 9.3 virtual machine, which comes pre-equipped with all of the software for running gates. We use a Linux Power Ubuntu terminal to open the folder containing all of the files necessary for the simulation, and the visualization is initiated by opening the main macro.mac file in VGate. When running the simulation, the maximum number of allowable events was set to 100, and we use root to read the outputs of the simulation. The simulation code that we use is organized into 3 folders: source, Mac, and outputs. The source file is going to contain all of the information and is going to import all of the VGate gamma emission packages and define how they are used within our simulation. The macro folder is going to contain a lot more. First, we have to import all the materials from a separate materials database, which is gatematerials.db. Then we add the commands to create a world, which is a cube with a length of 150 centimeters, and we set up the PET scanner volume, which is a 60 by 60 by 60 centimeter box made of air, where air was already predefined in our materials database. A visualization visu.mac file was added, which contained all the information about the scene and the viewpoint, which allowed us to easily view the scene when running GateQT. We create individual blocks, which are daughters of the mother PET scanner, and each block contains crystals of known dimensions. Each block is replicated and placed at different locations to form a cylinder shape suitable for imaging a human head. In this location, in this case, we decided that the X dimension of the crystal is going to represent the thickness, which is a key parameter that we're going to vary in the simulation. Within each crystal, we insert a repeat crystal, a cubic array that is composed of 4 parameters: repeat number X, repeat number Y, repeat number Z, and the repeat vector. The repeat vector is further divided into 3 parameters representing the X, Y, and Z repeat vectors respectively. Varying these values is going to change the number of pixels responsible for detecting gamma rays, which in turn affect the resolution and sensitivity of the PET system. In this report, we present the observed events, which are singles with varying crystal thickness. This detection efficiency is presented as the number of detected events. The source location includes details. The source code is going to also contain details about the forced unstable flag, which we set to true. And then we use a spherical volume type, which is with the activity set to 10 to the 5 BQ. A back-to-back gamma simulation with 511 kilovolts is simulated, and then the half-life is going to be manually set to 6,586.2 seconds, which corresponds to the half-time of the radioisotope 18F. In the main macro, we're going to also specify the physics processes that are necessary for running the simulation, which is standard model photoelectric, standard model Compton, Penelope model for Rayleigh scattering, standard model for electron ionization, and the standard model for E- and E+. And then we're also going to add in some multiple scattering values for our positrons and electrons in order to have the best model for positron annihilation. For the digitizer, we use a single digitizer with several parameters. First, the energy resolution is going to be 0.2 with reference values of 511 kilovolts, a time resolution of 71 picoseconds, and then we set the maximum and minimum threshold values to 650 kiloelectron volts and 350 kiloelectron volts. These parameters are all imported from VGate libraries. The simulated outputs include coincidental events, energies, and detection position, which are going to be used in our reconstruction, and we set the timing window to 10 nanoseconds with min sector difference set to 1. This means that for a successful event, the two singles have to be separated by blocks separated by at least one block. That means that they just can't be detected by the same block. We also set an offset of 500 nanoseconds to account for any insensitivities in the detector layer. The simulation is going to run for 1 second for acquisition, and then we're going to read and analyze the outputs using root. For 1,000 gamma emissions during the simulation acquisition, we're going to record approximately 500 singles, which are then going to be stored into our root file. Post-simulation analysis is going to use root to generate various figures and also to help us find the detection efficiency. It's important to note that while Gates provides the calculation of coincidences, the coincidence sorter is going to be disabled in this report. In real acquisition, you're going to want to use several key benchmarks, including the total count of generated events, their spatial and temporal distributions, the proportion of random and scattered coincidences, and the average angular deviations between two annihilation gammas. But due to constraints, we decided to only focus on the first factor, the total count of generated and detected coincidences. Over here, you can see how the actual full view of the visualization is going to look like. And over here, once we zoom in, you can see the individual blocks as well as the phantom, which is the blue volume that you see over there. So now going into our discussion and conclusions. So this graph is going to present the histogram of the energy deposited when gamma rays interact with the detector material. This interaction includes Compton scattering and photoelectric absorption, which deposit varying amounts of energy depending on the gamma rays energy and the detector material. We're going to observe that the largest peak is around 0.5 megaelectron volts, which is really close to our peak value of 511 kiloelectron volts. And we also see that the peak is very sharp and well defined, so that we know that we have a high sensitivity within our system. Now the key parameter that we want to vary, the crystal thickness. As the crystal thickness increases, the number of observable events is going to rise to approximately 520, which suggests that the maximum sensitivity and resolution are achieved for a 20 millimeter thick crystal. While a thicker crystal is going to enhance our sensitivity, to achieve a high resolution, we also have to incorporate depth of interaction. And while for now we decided to only evaluate the impact of crystal thickness on sensitivity, it would be also really important to explore other factors that affect the system performance, like pixel size by changing our repeat X, repeat Y, and repeat Z vectors, and the DOI information to improve our resolution even further. So now some acknowledgements. I really want to thank my mentor, Dr. Feng. She was incredibly helpful during during this entire 6 weeks. I actually got to meet her in person yesterday at Harvard. Even though I'm from Toronto, I was visiting Harvard. So that was a great experience. She was able to show me a lot around the lab. And I also want to thank Sabit Lab in general for providing me with all of the data that I was used, and especially its principal investigator, Dr. Hamid Sabet. Here are my references, and thank you for listening.
Yay, thank you so much, Daria. Okay, I'll stop recording.